the last lecture, I tried to talk a little bit about product kernels, singular product kernels. And so today I want to talk about beyond product kernels. This is a little nervy on my part. I would like to try to explain some papers of people in the audience. So what I would like to do is talk about some examples in which, first of all, product kernels arise, but then one does something more. One takes a quotient of that kernel, and one gets estimates, or the estimates on the kernel are, in some sense, better than just product kernels, and this will lead to flag kernels. So that's the sort of overall objective. So by the end of the lecture, I want to define precisely what flag kernels are. So the first example deals with joint multipliers in the Heisenberg group, and I'm now going to tell you, I hope, a little bit about a paper of Detlef Müller, Fulvio Ricci, and Eli Stein. And the idea here is to first lift to a product situation and then take a quotient. So I want to begin by reminding everybody or telling people about the Heisenberg group. The n-dimensional Heisenberg group Hn you can think of as Cn cross R, or sometimes as Rn cross R. And we use coordinates Zt if we're thinking about this in Cn cross R. Z, of course, is then an n-tuple, or x and y if I'm thinking in terms of Rn cross Rn. And one puts this multiplication, you define a product in this way. Now I just checked. I hope I have the plus signs and minus signs correct. We'll see. The identity element is 0, 0, that's easy to check. And the inverse of zt is minus z minus t. And there is a natural family of automorphic dilations in this group. If I multiply the first entry by z and the second entry by t, that would put a lambda here and a lambda here, put a lambda squared and a lambda squared in front of the t and s, and I would get a lambda squared coming out of this. So this is really an automorphic dilation. The corresponding homogeneous norm I can think of as the absolute value of z plus the square root of t, or if you want to make it smooth, it would be z squared plus maybe z to the fourth plus t squared and take the fourth root or something like that. Okay, now I want to just introduce some terminology. If I have an element in the Heisenberg group, then I can translate functions or objects by that. And I want to talk about either right or left translation here. I hope I have it right, and I hope I have it left. There's our translation on the left. So if w and s is a fixed point, I translate a function, L sub w s of f, at point zt, multiply zt on the left by ws. And if I have some operator which acts on functions, I'm going to say it's left invariant if it commutes with this translation. And now I want to use the real coordinates in the Heisenberg group, and I look at these, what last time I called vector fields or first order partial differential equations. There are n of the x's, n of the y's, and 1t, and I claim that these operators are left invariant in the sense that I just defined up here if I define the multiplication as I did here. I changed all the signs last night, so I hope this is right.
You were right at least once.
One or the other is correct. These vector fields satisfy certain commutator relations. What does the commutator mean? It means look at xj, xk minus xk, xj. In general, these operators don't commute with each other necessarily. Most of these operators do. You don't have commutation if you try to commute an xj with a yj. Then you get minus 4 times t. All right? Now, the object, the sort of analytic object that we really want to study, or I want to talk about, is the so-called Sup Laplacian, which I take these vector fields the x's and the y's, and I look at their squares, which gives me second order left invariant differential operators. And I form something like a Laplace operator. I put a minus here in order to make this a positive operator. Notice that we're dealing with this underlying space has dimension 2n plus 1, but we're really only dealing with 2n operators here, right? And now I claim that this operator is essentially self-adjoint and non-negative. If you integrate by parts, one sees that the inner product of L phi with phi is always bigger than or equal to 0. And by the spectral theorem, well, one can check that the operator L commutes with the operator T, because the coefficients of the various vector fields that I have don't involve T, so T always commutes with that. And so I can, by the spectral theorem, I can write down L and IT in terms of spectral measures, and these spectral measures will commute with each other because the operators commute with each other. And so what I can do is I can form, again, by the spectral theorem, I can form bounded operators on L2 by integrating the spectral measure against bounded functions. So if I have a bounded Borel measurable function, I can form a function of the operator L. The dE is the spectral resolution for L. dF is the spectral resolution for T. So I can actually have functions of two variables to have a function of both L and T in this way. And these are going to be bounded left invariant operators, and so they're given by convolution with certain distributions. And the question might be, under what conditions do these operators give us bounded operators in LP? And if they do, what is the nature of the distribution kernels that arise? Is there some way in which one can characterize these? So let me begin simply talking the sort of simplest case, a simple, relatively simple case, which is multiplier theorem for the Sup Laplacian. We simply look at operators that are functions of L. So in this case, what I'm going to do is I'm going to take a function of C which satisfies the usual kind of Calderon-Zygmund estimate for the multiplier, and I'm going to form the corresponding operator. And the theorem is that this operator is a left invariant operator on L2, and it extends to a bounded operator on LP for one P strictly bigger than 1 and less than infinity. And the operator is given by convolution. Of course, now this convolution is convolution on the Heisenberg group, not on a Euclidean space, but it's given by convolution with a distribution which is a Calderon-Zygmund distribution, and I've talked about those before. Let me remind you, nevertheless, what that really means in this case. Away from the origin, this distribution n is given by a smooth function. Again, I'm trying to use the same notation. Curly things, math cal is the distribution, ordinary m is the function. So away from the origin, it's given by a function which satisfies these characteristic Calderon-Zygmund type inequalities. Notice that differential with respect to x or y brings down a negative power of n, but t sort of is a second order operator, so it brings down 2 powers of that. So these are the differential inequalities for the distribution. I need also some cancellation conditions, and here it's expressed in terms, or one can express this in terms of the action on bump functions. I take a normalized bump function. To remind you, that means that it's a function supported in the unit ball. Say the supremum is less than 1, and the supremum of the gradient is less than 1. And I take any normalized bump function, dilate it according to the underlying dilation, and then the action of the distribution on that is bounded, independent of the bump function and R. And so here is the theorem. Now, the comment is this is really a one-parameter theorem, right? I'm dealing with, I end up with getting Calderon-Zygmund kernels. I wanted to say something about the background. I've only sort of just slightly scrape the surface. There's lots of work that's been done on this kind of thing, and I have tried to write down at least some of the names that are involved. I hope that this is sort of correct, that a lot of the focus of this work is trying to really understand the precise order of smoothness that one is dealing with. I've simply said, let's say, take everything to be C infinity, and I haven't worried about really the sharp questions here. Okay, so now let's talk about joint multipliers. Let's take functions of both C and tau. By the way, I should have perhaps said, when I'm integrating in C, C corresponds to the operator L, and that's a positive operator, so I'm integrating here for positive C. And suppose I take a function k of C and tau, which is homogeneous with respect to in both variables. Say here it has the same homogeneity. It turns out that in that case, again, this operator is given by convolution with a standard Kalman-Zygmund kernel. So the real question is, what happens if instead of taking functions which are jointly homogeneous, we take functions where we don't impose joint homogeneity, but we somehow allow separate homogeneity in each variable? So here's the problem. Suppose I take a function, a bounded measurable function, or here I'm taking C infinity, and suppose I only impose this kind of condition. This is sort of like the condition of the Marson-Cavendish multiplier theorem. Here's an example. If we look at m of a b, c to the a, tau to the b, c plus tau squared inverse, one can check that it's going to satisfy these inequalities, provided that the a and b are in a certain range. But here there is no single homogeneity. So this is really sort of a two-parameter question. And the theorem of Miller, Ricci, and Stein says that in this case it's still true that the operator m is bounded on LP for p bigger than 1, less than infinity, and m is a convolution operator. Now, capital M is a distribution satisfying certain differential equations and cancellation, differential inequalities and cancellation conditions. And I want to now look at what these are. What are the differential inequalities? So I take derivatives in Z and derivatives in T, and one notices that it's neither a product kernel nor a Calderon-Zygmund kernel. It's clearly still singular along a line. When Z is equal to 0, this blows up. But a typical product kernel would have a Z times a T. So it's somehow better in one aspect. So this is better than what one might expect. What are the cancellation conditions? Well, now we write down the similar kinds of things, or one way of saying this is to write down the kinds of estimates that we have when we talk about product kernels. I test the action of these functions against dilates of normalized bump functions. So I have to integrate against functions in T, and I get estimates in terms of R, integrate against functions in Z and get estimates in T, and do them jointly where I scale these separately. Okay, so here is at least one version of the kind of theorem that the three of them prove. But what I really want to sort of talk about is what goes into the proof. Now, I'm not going to give a proof, but I want to sort of outline what happens. And I think, in a sense, the key idea here is to lift the problem. The trouble is that on the Heisenberg group, there is no way of having homogeneity in Z and T which allows them to be independent of each other and have automorphic dilations. So one invents a larger group. In this case, we look at the Cartesian product of the Heisenberg group with R. And we let now the operator L act on the variables Hn, but we let IT act on the variables in R. These operators are going to commute with each other. They're going to have spectral representations just as before. And we can, again, form functions of L and IT. But now, on this group, Hn cross R, we have the natural dilations in the Heisenberg group, and also the natural dilations in R. And so, if I simply assume that I have a Marcinkiewicz type multiplier theorem, one can prove that the corresponding operator is really going to be a product kernel now on this new group G. Okay, what does that mean? Remind you what it means to be a product kernel here. Away from the diagonal, we have estimates. This is a product kernel type estimate on the Heisenberg group cross R. Here is the Heisenberg variable, here is the R variable, and it's simply powers of one times powers of the other. There are certain cancellation conditions. One has to integrate against dilates of functions in R and get a function of Z and T. One can integrate against dilates of a function in Z and T and get a function of U, or one can do everything together. And the condition is that what one gets is a singular integral, sort of one parameter singular integral in each of the variables that are unintegrated, or that one has uniform boundedness in the case that you're integrating against a double function of two variables. So, of course, I'm not proving any of this, but the idea is that by considering this product group and somehow lifting the problem of looking at these two operators to this product group, one gets a product kernel, which we've talked about. Now, what do we want to do? We want to be able to prove things about this lifted operator. So in particular, we'd like to know about LP bounds, and when we look at convolution. Now, what is the convolution here? It's the convolution on the group structure for Hn cross R, right? And because G has this natural two-parameter family of dilations, one can use a square function argument to prove that these operators really are bounded in LP. Okay, but of course, our original problem was not about the group Hn cross R, it was a question about operators on Hn all by itself. So what one wants to do, the idea is to look at this mapping which maps Hn cross R back down to Hn. This is a quite simple linear mapping, and the point is that I can pull back functions on Hn to functions on Hn cross R. I can apply this operator that I have on Hn cross R, and hopefully I will be able to then go back down again. And I've done the formal cancellation here. The idea is that the operator that I have up here is, let's see, have I written this right? I pull the function up to Hn cross R, and now I'm going to apply the operator t to this. Well, this is what it is. But the point is that because f is the pullback, I can put the integration in V inside, and what it looks like is an integral of f simply on Hn against a function of W and I'm sorry, yes, W and S, right? So what this really says is that the operator t that I had upstairs induces a convolution operator downstairs, all right? And again, I'm leaving out lots of hard work and details, but I think the idea is that the result follows by establishing three steps. One is that by going up, doing this thing, and coming back down again, I have an operator of the kind that I want. This is really the operator that I was originally interested in. The second statement is the standard transfer arguments show that because the operator upstairs is bounded in LP, the operator downstairs is also bounded in LP. But finally, what about the estimates on the size of the kernels? Well, I have a formula. I know product estimates for the function m upstairs, And if one is careful and clever enough, one can make estimates on the size of this, and you get the kind of estimates that I wrote down at the beginning, which are better than simply a product estimate. Okay? Yeah.
Could I, it's a naive question, but I've always been, when you lift, the new t isn't connected to L anymore.
That's right.
It's in this free variable W.
Right.
I'm missing something about how then, I mean, L is a Sup Laplacian. It needs a t.
Yes. Well, there is a t in the Sup Laplacian, right? Because I have coordinates zt and u. And now on this triple, I want to let the operator L act in zt. That's just on the Heisenberg group. And I want to let d by du act on the other. Now, I'm looking at this mapping. All right? Now, suppose I take a d by dt variable, d by dt derivative. That's sort of the same as taking a d by du variable. So it's this linear mapping which is finally linking derivatives with respect to u with the original derivatives with respect to t. And I skipped over this, but the key is the fact that the operator that I'm really interested in, which links t and L, comes from separating t and L upstairs, but then bringing them together this way. It's a miracle.
Yeah, it kind of strikes me like that.
Okay, so now I want to talk about a second example where something similar happens. I'd like to talk about some joint work with Stein on fundamental solutions for box B. And again, in this situation, the idea is to lift to a product, hope for a miracle. I love the cartoon, and at this point a miracle occurs, right? The only difference here is I want to say that the operators are not going to be translation invariant, so it's a little bit different. So what's the situation here? We have domains in Cn plus 1 of this form. I've written my variables z1 through zn and w, and I require that the, well, I guess I'm talking about a hypersurface. I'm talking about the boundary of the domain. The imaginary part of w is a certain function phi of z1 through zn. It's a real hypersurface with this defining function, and if you look at these differential operators, there are going to be 2n of them because I have the z's and the z bars. These will be, these annihilate the defining function, so we can think of these operators as acting on functions on the hypersurface itself. I can identify this hypersurface with Cn cross R. Simply to say that I'm in M is to say that my point has the form z1 through zn t plus I phi of z, and I simply forget about the phi. And then these operators take on this form, and it's really in this form that I want to think about them, so I'm really working in Cn cross R. I guess I should, it will come to this in a moment, but if I were to take this phi of z1 through zn to be modulus z1 squared plus modulus z2 squared plus modulus zn squared, these would be just the operators on the Heisenberg group, on the n-dimensional Heisenberg group. It's a little more general here. Okay, if we calculate that the commutator of the unbarred operators and the commutator of the barred operators is 0, but if I could try to commute a barred with an unbarred, I get this characteristic Hessian here. And what I'm interested in studying are second order operators of the form W1, W1 bar plus Wn, Wn bar, where each Wj is either an Lj or an Lj bar, and the other one is the conjugate. All right? So I don't know if that makes sense, but when n is equal to 2, there are 4 of them. All right? I can have them in various orders. Okay, I would love to be able to tell you that I can figure out what what one can do for an operator in generality, but can't, so we're going to deal with a very special case. Let's assume that the domain, the submanifold is decoupled. That means that this function can be thought of as a sum of functions of each of the variables separately. All right? In that case, if j is not equal to k, the two operators commute, and if they are the same, then basically the commutator is given by a multiple of the ordinary Laplacian. And one, from the point of view of complex analysis, one usually assumes that these phi's are subharmonic, so that we get positivity or negativity in each of these factors. Okay, so what do we want to do? We want to try to understand this operator, which is a sum of squares of various kinds of things. And the idea is we want to lift this to a product, just as was done earlier. So what are we going to do? We define surfaces nk in C2, where the imaginary part of wk is phi k of zk. And now I take the Cartesian product of these, which is going to be a subset of C2n. It's going to be a much higher codimension submanifold. And I can identify this with Cn cross Rn. And now the miracle mapping that before was just taking a sum in the two last variables now has this form. Okay? Notice that if I take a point in n sharp, pi then belongs to n, which was the original decoupled manifold that I'm interested in. Okay, we can now lift the operators. So I can think of these operators. Notice that instead of having d by dw or d by dw bar, these become the new variables that I've introduced. And I can either think of these as tangential operators acting on this submanifold in C2, or actually on the Cartesian product by having them only act on the appropriate variables. And let's look at the corresponding lifted operator, which means I simply look at sums of squares. Again, each one of these is either WW bar or W bar W, just as before. I would point out that, I hope I have this right, if I look at the inner product of this box sharp with phi, I get a sum of squares, so the null space of this box, formally the null space, is the intersection of the null spaces of these w's, right? We're going to do just what we did before. If f is a function downstairs on the manifold that I'm really interested in, I can pull it upstairs by composing with that mapping. And I claim that, that this mapping intertwines those two operators. This, again, I think is the key to what Jeff was asking. We now want to invert the operators upstairs. So how do we do that? I claim that we can find operators kj such that it commutes with each of these individual boxes and gives us the identity minus the projection onto the null space. You can't invert them because these things have a large L2 null space, but we have this. Each of these projections onto the null space actually is a singular integral operator on this two-dimensional, this submanifold of C2. It's given by integrating some kind of principal value integral against a function S, which satisfies Calderon-Zygmunt type estimates in terms of a certain metric that you can put on each one of the surfaces. And each of the operators that inverts or inverts modulo the projection is given by some kind of fractional integral operator of order 2. Now, and here I'm saying what I said a moment ago, there is a metric on each mj, on each one of these surfaces, so that I have these characteristic differential inequalities for my kernels, This is the singular integral operator, so if I'm not taking any derivatives at all, its size is 1 over the volume of the ball. This k is the smoothing operator of order 2, so if there are no derivatives, I'm improved by 2 factors of the distance divided by the volume of the ball. All right, the way one goes about constructing these operators is to consider the heat semigroup generated by this operator. It's given in terms of integrating against a heat kernel. And if this is sort of like the ordinary heat kernel in Euclidean space for the Laplace operator, but as s goes to infinity, this converges to the projection onto the null space. So what we want to do is we want to subtract that off, and then if I integrate from 0 to infinity, at least formally, I get a relative inverse to kj. Here I've written in terms of operators. Here I've written the same formula in terms of kernels. And the idea is that we can actually construct 2 different relative inverses for box upstairs. If I look at the projection, the product of the projections on all to the null spaces, this is really the orthogonal projection onto the null space of the full operator. Because these operators commute with each other, e to the minus the heat kernel, the heat semigroup factors as a product of heat kernels. And I can do one of 2 things. I can look at the integral from 0 to infinity of the this heat operator minus the full projection. This is given by this product. This s is given by this product. So I'm looking at the integral of a product minus a product. Or I can take each sj, subtract from the corresponding, and take the product. And these are both, in a sense, relative inverses to the operator that I'm interested in. What do I mean by that? The operator k sharp, this is actually the one that I'm really interested in, because it inverts modulo the projection onto the null space. But this other operator, n, inverts modulo the projection of 1 minus all of these, right? So this is a better inverse, but I've tried to say actually what's happening down here. These 2 operators, k and n, are related by a certain formula. Somehow the main part of k is n, but then there are other parts where some of the variables you have operators of type n, and in other places you have projections onto the null space. The thing to remember is that these operators n are sort of smoothing of order 2, right? All right, so here's the theorem. Suppose we take any quadratic polynomial in these differential operators, the so-called good directions, and I apply it to the relative fundamental solution n. Remember, n is the less good operator in terms of what my final objective is, but it's the better operator in terms of its behavior. And the claim is that this operator is a singular product kernel upstairs. On the other hand, if I apply an arbitrary quadratic polynomial to the kernel that I'm really interested in, well, one term is just fine, but then I have quadratic polynomials applied to these tensor products. And it could be that I'm putting some derivatives on the n or some derivatives on the Nagel projection, the corresponding Nagel projection. Derivatives, if all of the derivatives, 2 derivatives go on n, that's just fine. But if I put, say, 1 derivative on an n, this makes this smoothing of order 1. And I take 1 derivative of this is worse than a singular integral operator. So there's a difficulty here. One can deal with some combinations of these, and I've written down a lemma, but that's really not the focus. What happens, we have tried to do something upstairs, we now want to go downstairs again. So the claim is that I can push this operator that I call k sharp upstairs. I can push it down, and I can also push the operator n down. Formally, these are given by simply integrating the kernel that I had upstairs. I want to have a function of a single t, and I integrate them over the set where the sum of the tj's is that t. This is very much analogous to what was done in the earlier example. Okay, some final remarks. There's an analogous distribution n downstairs. This is very well behaved. Any quadratic derivative of n is going to be a bounded operator on LP. It's going to, because we had a product operator downstairs, we get a good thing downstairs. Only certain quadratic derivatives of k are bounded. And in fact, this shows that this box B fails to be maximally hypoelliptic. I guess there's a typo, there should be something in there. In some cases, we have a replacement for that maximal hypoellipticity. And another thing is that despite the fact that k sharp upstairs was singular along lots of subspaces, when one pushes it down, it turns out that what you have is singular only at the origin. On the other hand, it's not a Calderon-Zygmunt kernel. It has very strange estimates involving log terms and involving more than one distance, so it's rather a puzzle. So what's happened in these two examples? We have some problem in analysis. We want to try to understand it. We lift it to a product, try to solve the product upstairs, and then push back down again. And what I want to try to ask is what's really going on. Suppose I have a product kernel on some big space R capital N. Here I'm using the same awful notation that I introduced last time. Each of the RMJs has its own family of dilations, but since I'm dealing with product kernels, this is really an n-parameter family of dilations that I'm dealing with. Suppose I have a linear mapping from this big space down to some other space. In the two earlier examples, this was the example of Hn cross R down to Hn, or C2n down to Cn cross R in the second example, right? What I want to know is, can I push the distribution that I have upstairs down to a distribution on Rn? That's somehow what I've been doing in all of these cases. And to make the calculation a little easier, let's think of the following way. Let's let V be the kernel of this linear mapping, and let's choose a subspace W in Rn which complements that V. So I have the intersection 0 and the sum is Rn, and given any x in Rn, I can write it as a pair VW, and so on with pi VW is W. And let's suppose we've put measures on V and W so that I have a Fubini theorem here, all right? What I'm really asking is, given a distribution upstairs, can I get a distribution downstairs which satisfies this? Take a function, compose, and then try to apply the distribution. And of course, there's a difficulty. If I take a test function, when I compose with this linear mapping, I don't get something with compact support or doesn't decay at infinity. There's no reason to think, or one has to worry about whether this makes sense or not. Okay. Nevertheless, let's just plow ahead and see what happens. If I do this formally, what should the integral of k, I'm sorry, some of these are flat, some of these are sharp, so I got carried away. What should the integral be? Well, you write it all out and use the Fubini theorem, and one sees that in some sense the kernel, the distribution downstairs, should be simply the integral of the kernel upstairs over cosets of the null space. Let's try to make this a little more rigorous. Let's choose a compactly supported function in the V space. This is in the null space. We can dilate it by epsilon, and now if I have a function, test function in W, I can get a real compactly supported function in Rn by looking at the product. And now I can define a distribution which depends on what? On the choice of this cutoff function and this epsilon by looking at this tensor product. What's the idea? What happens is epsilon goes to 0, then this function, they all have compact support, but it looks more and more like just the pullback of psi all by itself. So I say, if the limit of these now are distributions, there's no difficulty. If the limit exists in the distributional sense, and if the limit is independent of the choice of this cutoff function, then we'll say we can push it down, right? So let's look at two examples. Well, one example with two subparts. Let's consider a triple Hilbert transform. This is much simpler than the examples that I started with. So this is integrated, this is a distribution, it's a principal value integrated with respect to dr over r, ds over s, dt over t. And now let's consider two cases. I have a distribution, it's a tempered distribution on R3. I want to map R3 into R2 by sending pi of xyz to xy. This is just projecting along one of the coordinates. I choose this cutoff function, I do the calculation, and what do I get? I get this. I get a double Hilbert transform applied to psi times the principal value of this. The epsilon has disappeared because I'm integrating dt over t, but the answer depends on chi. So in this case, I say I have some difficulty pushing things down, right? Let's deal with the second case. That's, again, pi of R3 to R2, pi of xyz is x minus z, y minus z. The null space is just the line x equals y equals z. If you do the calculations this time, one gets this formula. I'm sort of working formally here. One can take care of all of that. But what one sees is that now you're integrating a function psi against this kind of a function of R and S. But notice here, in t, this denominator decays like 1 over t cubed when t is large. And this chi is 1 on larger and larger intervals as epsilon goes to 0. So one can see that the limit as epsilon goes to 0, this actually converges, and at least formally, I have now a distribution where the kernel is given by this. If you think about what am I doing? I'm trying to integrate the triple Hilbert transform along certain lines. If I integrate along a line parallel to the original coordinate planes, I'm in trouble. And actually, that was used in the definition of product integrals. We had to do precisely this thing, and the requirement was that we had uniform estimates, but no limit. Or I can try to integrate over a line which is not parallel, in which case I do get decay at infinity, and I can push down. All right? However, let's look at the kernel that we get. What can I say about this as a function of R and S? If R is equal to 0, then I'm integrating dt over t squared. That doesn't look too good. If R is equal to S, then I have dt over s plus t squared. That doesn't look very good. And there's one other case which if s is equal to 0, again, we get difficulties. So what one notices that this kernel, which is what? It was a push down to R2 of a triple Hilbert transform. Triple Hilbert transform is the typical example of a product kernel. But when we push it down, we get a kernel which is singular along 3 lines, not 2. And it's not a product kernel. So we have to do something else. Or we don't have to, but So here is the remark that if I project along something parallel to one of the axes, this already occurred in the definition of product kernels, but it does not require that the limit be independent. And then I just made another remark. I've talked about trying to push down distributions. Another way of thinking about this is trying to restrict the Fourier transform to subspaces. It's sort of a dual way of thinking about this. So what one wants to do is to introduce the notion of flag kernels, which is a more restrictive class and which behaves better under this quotienting process. So what is a flag kernel? A flag, first of all, for us is simply an increasing sequence of subspaces in Rn, and we'll say that we have a flag of length little n in R capital N if there's a sequence of n in little n increasing subspaces.